If I prepared something, no, but before we start that, are there any questions that you have? May mga tanong ba? Okay, I encourage you to review the material that is distributed to you before going to class, because remember that in these sessions, I'm going to only discuss parts of the material which I think might need more explaining. So I don't have time to discuss all the material, and it's going to be difficult for you to keep up if what I'm going to say is the first time you're going to read or hear about what I'm talking about. So I really encourage you to read the handouts, the materials, before you go to our supplementary lectures. Okay. Okay, I'm going to backtrack a bit. I'll talk a little bit about what we were able to cover last week. And then I'm going to go to the main topic for today, which is PN junctions. So let me share my screen. Okay, if you have any questions, please feel free to interrupt me anytime. So last time, we didn't get the chance to discuss this much, but we were talking about conduction mechanisms. In semiconductors. Okay. And the first conduction mechanism that we talked about is drift. And this is the tendency of charges to move in the presence of an electric field. So let's say I had a semiconductor material, and I have, let's say, electrons in this material, and I also had holes in this material. Okay. So if I had an electric field, for example, in this direction, okay, what direction will my electrons move and what direction will my holes move? Anyone? Can I hear a shout out? Saan pupunta yung electrons ko, saan pupunta yung holes ko?
Sir, yung holes po sa direction ng electric field, yung electrons naman po sa opposite ng electric field.
Yeah, that's good, no? So the electrons are going to go this way, and then the holes are going to go this way, no? Okay, I have current due to two components, no? I have current due to electrons, I due to N, and I due to P. Okay, my total current will be IN plus I sub P. And my current due to electrons and my current due to holes will be in the same direction, no? Because if electrons are going to the right, then current described as the flow of positive charges will be going to the left, and then holes are considered positive charges also going to the left. So my total current will just be the sum of these two, which will be in the direction of the left side. Okay, we define current density as J. And this is current per unit area. In other words, if I have a cross-sectional area A, if this is area A, my current density will be equal to I over A. Assuming that my current is uniform throughout the cross-sectional area, no? Then my current density will be I over A. Okay, so I have J. Okay, so this is drift current, no? This is a drift current. I have J N due to drift. This is the current density of due to the drift of electrons. Okay, this is going to be Q N, okay, muse of N times the magnitude of my electric field, no? Where Q is my is the magnitude of the electronic charge. Q is the magnitude of the electron charge. And then N, we know what N is. This is your electron concentration. Okay. And then muse of N, this is what we call the mobility of your electrons. So your Q is in coulombs. Your concentration is in number of electrons per cubic centimeter, and your mobility is centimeters. This is centimeters squared over volt second. Okay, and then E is equal to your electric field intensity. This is volts per centimeter. And then you have J P due to drift, and this is Q P muse of P times E. No, where the only well, of course, P is your whole concentration, and then itong muse of P, this is your mobility of your holes. And your J drift is Jn drift plus Jp drift. So if I combine, you have Q, you have N muse of N plus P muse of P multiplied by the magnitude of E. Where this term is now called your conductivity. And sigma is equal to 1 over rho, where rho is your resistivity. Now, what exactly does mobility describe? Mobility describes, kumbaga parang gaano kaliksi yung charge carrier, ano? It describes the magnitude to which your charge carrier can move in the presence of an electric field. So, for example, the mobility of electrons, this will be larger than the mobility of holes. It's much easier for electrons to move than for your holes to move. As a matter of fact, the mobility of electrons is typically 2.5 to 3 times the mobility of holes. In other words, in the presence of an electric field, expect that that there will be more electrons, or the electrons will be capable of moving faster than your holes. So that is drift. Let's go to diffusion. So this is your second mechanism for conduction, diffusion. So this is the tendency of the concentration of carriers to become uniform within a volume, over time. Okay, the easiest way for me to describe diffusion is, I don't know if I made this analogy before. If you have water, and you drop ink. Okay? Initially, pag pinataka mo ng ink yung tubig, you're going to see the ink, ano? But as time passes, what will happen? The ink will disperse throughout the volume. And after a long time, halos wala ka na makikitang tinta. This is if it's one drop. Of course, if you drop several drops, then it might change the overall color of the water. But eventually, the color of the water will become uniform. You know? That's because of diffusion. There's going to be a high concentration of ink at a particular spot, and then as time passes, the molecules making up the ink will diffuse toward the entire liquid, and it will become uniform. So ganun din yung nangyayari sa charge carriers. If there's a non-uniform concentration of charge carriers, and there's no, there's no electric field to speak of, there's no excitation, then the tendency within the volume is for the charge carriers to become uniform. Okay, let's consider a particular situation. Let's say I have a solid, and then I manage to inject carriers into one end of the solid. No? So for example, dito sa end na to, let's say I manage to inject holes. No? Okay, there are many ways of doing this. No? One way of doing it is by heating this particular surface. So if you heat that surface, you're going to generate electron hole pairs, so you're going to have excess holes. No? Another way is through illumination. Another way later on is you're going to find is in a PN junction there's a minority carrier injection. No? But what will happen? No? Let's say I inject holes. If I plot the whole concentration over distance, so this is the whole concentration over distance. No? So this is X. Okay, what's going to happen here is, okay, so dito, no, there's a constant injection of holes. I'm going to end up getting an exponential profile. There's going to be an exponential profile, no? Exponential distribution of holes. Okay, my holes are going to move toward the right. Why? Because my concentration here is high. So because the concentration here is high, that is going to make my holes move toward the right. No? But it will, as you move toward the right, it will never be higher than where it came from. It will always be lower. And that's what will cause this drop. You know? Okay. This is now what we call diffusion. No? This is holes. This is moving because of diffusion. My JP, due now to diffusion, is going to be proportional to dpdx. No? Where dpdx is the rate of change of P with respect to X. Okay. However, dpdx is actually decreasing. And my direction of current flow is in the direction of decreasing dpdx. No? So current flows in the direction of decreasing dpdx, or of negative, sorry, not of decreasing, of negative dpdx. That's why JP diffusion, the formula for that is actually going to be negative, no, because current flows in the direction of negative dpdx. Negative, you have Q dp by dx. Q dp by dx. But if you get the corresponding equation for electrons, nawawala yung negative sign. This is going to be minus, this is going to be, sorry, this is going to be Q dn by dx. And the reason for this is because the direction of current when it is electrons is opposite the direction of electron flow. So the negative becomes positive. So this is diffusion current due to electrons. This is diffusion current due to holes. Now dp and dn, these are what we call our diffusion constants. Okay. And then your total diffusion current will just be equal to Jn diffusion plus Jp diffusion. Okay, when there is an electric field and at the same time non-uniform concentration, then your J total will be equal to J diffusion plus J drift. So this will be due to your electric field, and this will be due to your non-uniform concentration. Are there any questions? Any questions? Okay. Let me give an example of this. Example of this. Let's consider a non-uniformly doped N-type semiconductor. Let's consider a non-uniformly doped N-type semiconductor. So if this is my semiconductor, so just try to imagine, let's say this is more heavily doped. The left side is more heavily doped than the right side, no? So here it is quite heavily doped. And then here it is lightly doped. Now let's assume that the doping profile is linear. So let's assume a linear doping profile. Okay? So this is my doping concentration. Kunwari lang, no? Kunwari, pag ganyan siya. Okay. So if my semiconductor is completely ionized, and I described what complete ionization was last time, ano? That is, if this is N-type, completely ionized means all of the donor atoms will have electrons that are promoted to the conduction band. Then this is going to be my N versus X. No? N versus X is going to follow my doping profile. And because of that, there's a non-uniform concentration of electrons, and therefore expect that electrons will diffuse. Electrons will diffuse to the right. Now, what's going to happen when your electrons diffuse to the right? No? As your electrons leave the left side, that part is going to be positively charged. Kasi meron kang electrons doon dati, no? Remember, the left side used to be neutral. So this part used to be neutral. Now you have electrons that are leaving this part and going toward the right. So habang umalis dito yung electrons, nagiging positive to, no? Samantalang habang lumilipat yung electrons from the left to the right side is becoming more and more negative. No? So that at some as your electrons move, no? This will be positive kasi umalis yung electrons. And then, of course, as you go to the right, it gets less positive until it starts getting negative. And then it starts getting more and more negative. No? So nagkakaroon ka ng charge distribution. No? There's an uneven charge distribution. Of course, overall, this is going to be neutral because the amount of positive charge is going to be equal to the amount of negative charge. But inside, there's an uneven charge distribution. If the left is positive with respect to right, you have an electric field that will now build up. So as your charges are moving, this electric field will build up. Now, what did we say happens when there's an electric field? Ano nangyayari pag nagkakaroon ng electric field? Anyone? What happens when you have an electric field? We just talked about it, no, just a few moments ago. What will happen? What will happen? Yes? Anyone?
Mag-move po yung electrons ulit tsaka yung holes.
In what direction?
Yung electrons po opposite ng electric field and then yung holes along the electric field.
Okay, that's good. No? Thank you for your answer, Jason. No? So, kung meron tayong electric field ngayon, magkakaroon tayo ng drift. No? And your electrons will drift now toward the left. And then your holes will drift toward the right. Right? So because of the non-uniform concentration, you have diffusion, electrons diffusing toward the right. No? Sorry. Wala pala tayong holes dito. This is N-type. Sorry, I'm a little bit confused now. No? This is just N-type. You only have electrons. We only have electrons because this is n-type. Okay, so because of the electric field, your electrons will drift toward the left, ano? So dati may rather, no, because of non-uniform concentration, may diffusion tayo toward the right, but because of this electric field, there will be drift toward the left, no? So the I diffusion will cancel out the I drift. And at equilibrium, I total will be equal to 0. That's what will happen. No? And of course, there really won't be any current because this is an open circuited semiconductor material. Wala naman nakakabit sa kanya, no? So how can there be any current flowing when there's no nothing? There's no excitation, there are no sources, there's no anything. Okay, but when you reach equilibrium, this electric field would have built up to a certain value, no? And this electric field causes a potential difference. There's a potential difference because of the electric field. For positive charges, the left side will be of a higher potential than the right side. No, this is for sorry. For yeah, no, that's right. For positive charges, the left side will be of a higher potential than the right side. But for negative charges, if we're talking about the potential energy for electrons, the right side is going to be of a higher potential than the left side. No? So this is going to cause a voltage. The voltage is going to be positive on the left side, negative on the right side. But if we're talking about electrons, that means your energy of the electrons on the right side would be higher than the energy of the electrons on the left side. No? This is because of the voltage drop. Okay. So what is going to happen? No? So the difference. I need an extra sheet. No. Okay, the electric field will make energy of electrons on the right side higher than on the left side. That's what's going to happen. No? And this will affect the energy band diagram. If I plot the energy band diagram, so this is versus X. No? So let's say this is the end of my solid. So I have EC, and then I have EV. Okay. If my doping profile is linear, then my energy bands are going to bend upward. So the energy bands are going to bend upward. Okay, that's what's going to happen. Okay. Of course, my my Fermi energy. So this is going to be my Fermi energy. This is going to stay uniform. E of F stays uniform. Okay. Are there any questions? So this is what you call band bending. This is how your energy band diagram is going to look like at steady state. Okay. Let's go to the discussion, which was the real intent for today's session, and this is PN junctions. There's a question, and by the way, if you have a question, I would prefer that you interrupt me because sometimes I don't see the chat. Would you like to voice out your question, Andre?
Sir, what does it mean po for the energy bands to bend upward?
Yun, pag nag-bend upward, ibig lang sabihin no, habang pumupunta ako dito sa kanan, it will take a larger amount of energy for my electron to be promoted to the conduction band. No? Kasi kung meron akong electron, for example, electron dito, no? I have an electron here, and I want it to be promoted to the, well, if I had this amount of energy, no? If my electron had this amount of energy here, and I wanted it to go to the conduction band, then all I need is to overcome this gap, no? And then it will already be in the conduction band, no? But here I have to overcome a bigger gap if I have the same amount of starting energy. No? On the other hand, if I have an energy that is already here, if I have an electron that's already here, this is the value of my potential energy. That means as I go toward the right, it will be increasing in kinetic energy. It will be traveling faster. But if I go toward the left rather, so yun ang ibig sabihin nun, no? Did I manage to answer your question? Or is it vague?
Try ko po muna siguro i-digest, sir. Thank you po.
Yeah. Kasi remember E of C, that is the E of C is the minimum energy that the electron has to possess for it to be able to break away from its covalent bond, no? And become available to conduct current, no? Basically, that's E of C, no? And this is with respect to X. This is with respect to X. So ibig lang sabihin yan, as we go toward the right, the minimum amount of energy needed by an electron to break away from its covalent bond will be higher. Okay. Anyway, try to digest that, ano?
Sir,
Okay,
magtanong po
let's.
ako dun po sa previous slide po.
Yes.
Bali, yung electric field po ay going to the left. Tama po ba? Dun sa nagbe-bend po na diagram na energy band.
Ito yung nangyayari, no? Yung electric field is going from left to right. Okay? But these energies are described for electrons. And electrons have a negative charge. Okay? So if electrons are of negative charge, then ang high potential niya baliktad sa, for example dito, no? Here your electric field is left to right, no? So for positive charges, mas mataas yung potential mo sa kanan kaysa sa kaliwa. No, that's what you mean by potential drop. Remember, it's a triple E 1, 2, 3. You have a potential drop. You have a potential difference between the left side and the right side. The left side will be of a higher potential than the right side. No, naalala niyo yun, ano? But that is defined for positive charges. No, that is defined for positive charges. Pag negative charge, iba, no? If you have a negative charge, that means the energy that charge possesses, if it is at the right side, will be higher than at the left side. No? And the energy band diagram is defined for electrons. That is why your energy at the right side for electrons will be higher than the energy at the left side. Nakuha mo ba yon?
So bali sir, tatandaan ko lang po. Bali mas malaki yung energy sa left kumpara sa right. In simple terms po, ganon.
Mas malaki yung energy.
Wait,
what do you
kukubos ko po muna.
No. The energy of your electron has nothing to do with the energy band diagram, ano? The energy of your electron may be, for example, this can be the energy of your let's say this is the energy of your electron, no? Ang sinasabi lang ng energy band diagram is how much energy do you need for this electron to conduct electricity. So for this electron to conduct electricity, that is to break away from this covalent bond, it has to have at least this amount of energy. On the other hand, if this electron with the same amount of energy were here on the left side, it will only need this amount of energy. So it's not the energy possessed by the electron. No? We're not talking about energy possessed by electron. We're talking about the energy needed by the electron to be able to conduct.
Okay po sir, gets ko. Ang siguro po, nalito lang po ako nung papunta na sa upward, yung napag-aralan po natin nung nakaraang linggo, is pantay lang po, di ba? Ngayon po, nag-upward na siya. So, inaalam ko pa rin po kung ano yung difference, bakit upward yung isa man flat lang.
Hindi lumalaki yung energy ng electron, ano?
Apa.
It's the energy needed for the electron para umakyat. And by the way, no? Somebody asked me this question last time after class, ano? Ano bang ibig sabihin ng umaakyat sa conduction band, no? And I told him, don't think of it as physically jumping, no? Because wala naman yung layer sa solid na walang layer yan sa solid na kailangan umakyat ka dun sa layer na yun para mag-conduct ka, no? When I say umakyat sa conduction band, all I mean is it will now gain enough energy so that it can roam the entire solid and is not bound to the nucleus, no? Because if it is a valence electron, if your electron is a valence electron, no, that means nakakapit siya dun sa nucleus, hindi siya makalibot, no? But if your electron becomes a free electron, that means it can go throughout the entire solid. It has enough energy to go throughout the entire solid, no? Nakakalibot siya. So don't think of it as a place in the solid where it jumps. It's more a state. It's the state of the electron, whether the electron can conduct or the electron cannot conduct. That depends on the amount of energy that electron has. If it has low energy, nakakapit lang siya sa nucleus. If it has high energy, it will be able to conduct. It will have enough energy to roam the solid. Okay. So I hope that doesn't confuse you. No? Okay, let me go to PN junctions. Okay, how do you create a PN junction? Okay, we start with typically you start with an N-type. No? Okay, so this is an N-type. And then at one end, you introduce acceptor impurities. At one end, you introduce acceptor impurities. Now, this is done during the fabrication process. Usually you do it in what is called a diffusion furnace or diffusion oven. No? So you have the N-type there, and then in the diffusion oven, you introduce the donor impurities, and you do it in such a way that only one surface is exposed to the. You introduce the acceptor impurities, rather, no, and you did it in such a way that only one surface is exposed to the acceptor impurities. And those acceptor impurities, well, this is all done at the high temperature. Those acceptor impurities will start replacing atoms here in the left side. No? And as time goes by, it will encroach further and further into the semiconductor material, much like diffusion. So it's very similar to diffusion. And if you take a look at the diffused acceptor concentration. So let me try to plot the, let's say this is the diffused acceptor concentration. It's going to look something like this. It's going to be a bit, it's going to be exponential. Sorry. So it's going to be exponential. No? This is the diffused acceptor concentration. So you diffuse acceptors. This is the second step, no? Diffuse acceptors, acceptor impurities at one end. Now let's say this was the original donor impurity concentration. So this is my diffused acceptor concentration. This is my original donor impurity concentration. If I get the net donor concentration, so this is now my net donor concentration. So what is this, no? This is just going to be ND minus this. So my net donor concentration is my original concentration minus my diffused acceptor concentration. Ang lalabas niyan, that is going to look like this. So here, my concentration is going to be, my net concentration is going to be 0 because they're equal. No, the injected and the original are equal. Here it's going to be negative, and here it's going to be positive. So this is going to be ND. This is going to be ND. Kasi dito nagiging 0 na, no? Pag naging 0 na, your concentration is going to be ND. This is going to be minus NA, where this is NA. No? The difference between my injected acceptor and my original is Na. So this is going to be minus Na. Okay. So I redo it here. No? This is minus Na and this is Nd. So the left side, sorry. If I take a look, oh, this happens. This is going to end up being p-type. And the right side is going to end up being n-type. Now, ideally, I would have wanted the concentration to look like this. Ano? This is the ideal. Okay, this is what we end up with. No? This is what we end up with. In our analysis, we're going to assume this is the profile. And it can be shown later on, although we're not really going to show it, no? But it can be shown through various references, that when we analyze, assuming this profile, hindi na masyadong malayo sa katotohanan, ano? That is, if this had been the profile. The results are very close to each other. Okay, so this is now what we call our PN junction. The point at which the semiconductor material transitions from p-type to n-type is our PN junction. Note that you cannot create a PN junction by just gluing together a p-type and an n-type. It has to be a single crystal. The entire solid has to be a single crystal with one side predominantly p, in fact p, and the other side n. Okay, this is the energy band diagram of the PN junction at the instant it was created. So let's assume that, okay, I magically was able to create a PN junction at that particular instant that it was created. This is how the band diagram of your PN junction is going to look like. So you have your EC, you have your EV, you have your intrinsic concentration. So you remember EI is your intrinsic Fermi level. No? EI. This is your intrinsic Fermi level. And this is just equal to 1/2 of EC plus EV. This is the midpoint between EC and EV. Then if you recall, if you have a p-type semiconductor, your Fermi energy level becomes in between EI and EV. And if you have an n-type semiconductor, your Fermi energy level becomes between EC and EI. No? So sa n-type, umaakyat yung Fermi level natin. Sa p-type, bumababa yung Fermi level natin. Now, what will happen when the PN junction is first created? So this is the instant after it is created. Okay, this is going to be n-type, this is going to be p-type. There's going to be diffusion. So what will happen is you're going to have holes diffusing left to right. So may mga holes na mag-diffuse dito, no? And then you have electrons diffusing right to left. Okay, remember this is p-type. This is n-type rather. This is a single crystal. So the concentration of N here will be high, the concentration of N here will be low. So naturally your holes will diffuse from right to left, and vice versa. No, your electrons will diffuse from right to left, and then your holes will diffuse from left to right. Okay, what will happen when an electron and a hole meet each other? What do you expect to happen? Anyone? Anong mangyayari pag nagkita isang electron sa isang hole?
Ma-occupy po ng electron yung hole.
That's right, no? The chances are the electron will occupy the hole. And therefore, both the electron and the hole will disappear. Right? So, ang mangyayari, okay, yung electrons dito, papunta dito sa kaliwa, yung hole dito, papunta dyan sa kanan. Eventually, magkakaroon ng area rito na nawala na yung electrons at saka holes, no? So if I draw now my solid, there's going to be a region here. Okay, so this is going to be p-type. This is going to be n-type. There's going to be a region here that is depleted of either electrons or holes. That's somewhere here. And this is what we call your depletion region. In the depletion region, N is approximately equal to P, which is approximately equal to 0. N approximately equal to P, approximately equal to 0. Okay. Kung yung electrons dito pumunta dito, no? So let's say I have electrons here that went here. What is going to happen to this area? This area, kasi inalisan siya ng mga electrons, is going to be positively charged. So this area will be positively charged. This is my junction. On the other hand, yung electrons ko rito, pumunta dito, so ngayon sobra yung electrons dito. Initially, this is neutral. Initially, that is neutral. So yung electrons dito umalis, pumunta rito, nagiging positive to, okay, kasi nabawasan siya ng electrons. Ito naman, nadagdagan ng electrons, kaya magiging negative to. So what happens when you have a charge distribution such as this? So meron akong charge distribution dito. Ang mangyayari rito, I'm going to have now an electric field in this direction. Okay, I'm going to have an electric field in that direction. Okay. Now what will happen? What will happen if you have an electric field? So one of you already answered earlier. Whenever you have an electric field, you are going to get drift. Okay, is it possible for there to be drift? What is drift? No? Drift is electrons flowing opposite the electric field and holes flowing in the same direction as the electric field. So are there electrons from the p side that can go to the n side? No. The answer is yes. Because you have what are called intrinsic carriers. Intrinsic carriers, those are carriers that are intrinsic to the material. No? Kahit na hindi siya p-type, there would be intrinsic carriers. In fact, they would be electron-hole pairs, no? Because of thermal energy. So meron tayong electrons dito sa p-type, kahit na p-type siya, meron tayong intrinsic electrons dito that because of the electric field will go now toward the right. And you will have holes on the n-type, intrinsic holes, that will go toward the left. Okay, so the electric field will cause electrons to drift right and holes to drift left. Okay, at equilibrium, okay, the diffusion will be equal to the drift, no, and I total will be equal to 0. Okay. Okay, I total will be 0. Kasi yung electrons, for example, are diffusing, no, are diffusing right to left. That's the electrons diffusing right to left. Pero yung electrons naman are drifting left to right. Okay? So yung net flow ng electrons magiging 0 at equilibrium. Ganun din, no? Yung holes mo naman baliktad, no? Yung holes are left to right, diffusion, right to left drift, so magiging 0. So at equilibrium, this is going to be 0, which makes sense kasi it's just a piece of semiconductor material. So how can there be a current that will flow? It's an open circuit. Okay. Okay, so that is what happens. Now, because of this electric field, from the perspective of positive charges, you have a higher potential on the right side than on the left side. But from the perspective of negative charges, you have a higher potential at the left side than at the right side. No? So ang mangyayari niyan, okay, across the depletion region, magkakaroon ka ng band bending. Remember we talked about band bending earlier? Ang band bending natin, yung kanan bababa with respect to the right, ano? So parang bababa siyang ganyan, no? So this is original, and this is what will happen. So sorry about that. So this is now my depletion region. This is my depletion region. And from the perspective of electrons, because my energy band diagram is from the perspective of electrons, my right side will have a higher energy than will have a higher value of EC and EV. No? Maybe you get confused because I say energy, no? But my right side will have a higher value of EC and EV than, my left side rather will have a higher value of EC and EV than on my right side. No? So what actually happened was, okay, itong part na to, nahatak pababa para yung Fermi level natin, our Fermi energy level, becomes a single value, which is a condition for equilibrium, no, for any solid. That a solid at equilibrium, at thermal equilibrium, can only have one Fermi energy level. Are there any questions? So this is how your energy band diagram will look like when you have a PN junction. Are there any questions? Okay. So I guess I already mentioned this. No? So dun sa depletion region, ang value ng N at saka P will be equal to 0. Okay, the difference, the amount by which the energy shifts, no? The energy band shifts, there's an empirical formula for that, and that is given by this. Ano? First of all, this is an energy. So energy is equal to voltage times current. No? Energy is equal to charge times voltage, no? Not voltage times current. Energy is equal to charge times voltage. Voltage is joules per charge, and therefore you multiply joules per charge by charge, you'll get joules, which is energy. No? So this is an energy, and that is equal to this expression. K is Boltzmann's constant, T is your temperature in degrees Kelvin, and the Na, you know that's your donor concentration and acceptor concentration. So the donor concentration is of the N type, the acceptor concentration is of the P type, and Ni is your intrinsic carrier concentration. VBI, we call this our built-in potential. That is the amount, the equivalent amount in volts that the energy band shifts. Okay, so this is equilibrium. Okay, now this is no longer equilibrium because we are applying an external voltage. Let's apply an external voltage to our PN junction. So here I exaggerated this is the depletion region. I exaggerated it. Actually, this is just usually a very, very small portion of the, this is a very, very narrow part, no, within the junction. And the reference polarity for the voltage that is applied is the P side being positive with respect to the N side. And the value that we should apply should actually be lower than VBI. So this is VBI. Okay. That is for low-level injection. Usually, you're not going to. Usually you will never apply a voltage directly to a PN junction. You will always do it through a resistor, no? But in this particular case, let's just assume that we can apply this voltage, and it will affect the band diagram directly, no? So what will happen if V sub A is positive? So these are our equilibrium conditions. If you apply a positive voltage, okay, the first thing that's going to happen is, okay, this is VBI, no, this is rather Q VBI. This is going to be equal to Q VBI minus VA. So yung energy bending is going to be less. And then my W prime is going to be less than W. My depletion region is going to become narrower. So liliit, no? Liliit tong ito, no? This one is going to get smaller. On the other hand, what if I apply a negative VA? What if I make my P side more negative than my N side? Okay, this is the original. This is VBI. Again, Q VBI. This is going to be Q VBI plus VA. So lalaki. This is going to be bigger. And my W prime is going to be bigger than W. In other words, my depletion region is going to get wider. Lalapad yung depletion region ko. So that is the effect of biasing. We call this forward biased when VI is greater than 0. And we call this reverse biased when VA is less than 0. Okay, so qualitatively, how is that going to affect the flow of current? Okay, so this is at equilibrium. Walang naka-apply na VA. No? Walang naka-apply na VA. In other words, open-circuited. This assumes that open-circuited yung junction ko. These are the energy states of my free electrons. These are the energy states of my holes. Okay, the energy states of my free electrons, the energy states of my holes. Okay, let's take a look at the left side first. So tignan lang muna natin yung electrons. So what is this? This is an electron in the p side, meaning to say this electron is an intrinsic electron. No? Because if you have an electron in the p side, that means these are thermally generated. These are from thermally generated electron hole pairs, and therefore it's an intrinsic electron. Okay, so this is an electron on the p side. Is this capable of going to the n side? Yes, it is. No, so this is capable of drifting. Right? It has enough energy. Well, it's already in the conduction band. No, and if you go toward the right, okay, it will have. In fact, if you go toward the right, it will have more kinetic energy. No, it has more than enough energy to roam the entire solid. No, so this can drift to the right. So this will only move in the presence of an electric field. And remember, dito sa depletion region, you have an electric field. In the depletion region, you have an electric field that is going from the left to the right. No? There's an electric field this way. Where did I show that? Here, no? There's an electric field that is going from the left to the right. So this if it is in the vicinity of the depletion region, will actually fall down this hill, no? Yung tinatawag nating mahuhulog dito sa hill na to. Okay? It can drift to the right. Now this particular electron can diffuse to the left. Right? If you take a look at this electron, it has enough energy to go to the left, no? Because its energy is higher than the blue line. Okay? But if you take a look at these electrons here, ito mga electrons na to, this cannot diffuse. By the way, no, why diffusion? The action here is diffusion because here we have a high concentration, here we have a low concentration. So the action here is diffusion. Why cannot this diffuse? No? Because if this tries to go to the left, it will not have enough energy, no? Para siyang umakyat ng hill, it will not have enough energy to go up the hill. No? It will get stuck. So this cannot diffuse. So ito nakaka-drift papuntang kanan, ito nakaka-drift papuntang kaliwa. Okay, the diffusion is equal to the drift, and your net current is equal to 0. So your diffusion is equal to drift. I will be equal to 0. And you can make the same analysis for the holes. So this hole can drift, this hole can diffuse, but these holes here cannot diffuse. And therefore you have one electron that can drift, you have one electron that can diffuse. They cancel each other out. Your net current will be equal to 0. Okay, tignan naman natin kung forward biased. So kung forward biased, this can drift. This can drift. Okay, lumiit ito. So dati-dati itong dalawa hindi kaya mag-drift. Pero ngayon, itong tatlo kaya na mag-drift. This can drift. Sorry, this can diffuse. Sorry. This can diffuse. Itong tatlo still cannot diffuse. Still cannot diffuse. No? But now notice that more electrons can diffuse than can drift. So here your diffusion will be greater than, this is the magnitude of your diffusion, will be greater than the magnitude of your drift. So you have a net current flowing, you have net electron flow from left to right. There will be a net electron flow from left to right, or a net current from right to left. No? So there's going to be a current here due to N. No? In the same way, ganun din dito, no? These three can diffuse, only one can drift. So there's going to be a net whole current flowing from left to right. That's because your diffusion is greater than your drift. Now let's take a look at the reverse bias. Your reverse bias, lumaki to. This one can still drift. But now, none of this can drift, no? None can drift. Okay? Meaning to say, you have electron flow from left to right, you have a net current this way, IN. This is IN this way, no? Because this can drift, none of this can. Sorry about being confusing. No? None of this can diffuse, not drift. No? None of this can diffuse. This can drift. No? This can go toward the right, meaning to say that you have a net current going to the left. No? Okay. The same way you also have a whole current going to the left. Okay, so when it's forward biased, you have a diffusion current. Okay, and the direction is from left to right. And when it is reverse biased, you have a drift current from right to left. But this current is very, very small. And the reason why that's very, very small is because the carriers are due to intrinsic carriers. The only carriers that will contribute to the conduction of electricity are the thermally generated minority carriers. So these are thermally generated electrons on the p side and thermally generated holes on the n side. Okay, so if you take a look at the diffusion current, let's take a look at the diffusion current components. So let's say this is our junction. This is the junction. This is your N type. This is your P type. And let's say this is my depletion region. So this is my depletion region. So as we mentioned earlier, in the depletion region, N equal to P equal to 0. If I take a look at the value of N here on the left, at the far right, that will be equal to N's of D. This will be equal to N's of D, donor impurity. And as soon as well, the electrons from the N side are going to sweep across the depletion region, and then are going to end up on the P side, okay? And as soon as they emerge from the P side, okay, it's going to fall exponentially. So this is going to be my electron concentration on the P side due to diffused electrons from the N side. And I might have a similar situation for my holes. Let me use a different color. So for holes, for example, this can be Na. Let's say this is Na. And then starting here, this is going to drop this way. So this is going to be the concentration of holes on the N side. So note that these are minority carriers. This is my concentration of holes on the N side. This is the concentration of electrons in my P side. So this is what is going to cause diffusion. So here, because there's an uneven concentration, then you're going to get electrons diffusing. Electrons diffusing this way, meaning to say your current is this way. No? On the other end here, you have holes diffusing this way. No? Also a current flowing this way, because your current direction is equal to the direction of flow of holes. No? So net, I have a current flowing from my P type to my N type, and that is due to diffusion. And the relationships, we're not going to go through the derivation of the current that will flow. No? We used to do that, but we decided not to do it anymore here. The relationship that will come out is exponential in nature. As a matter of fact, the relationship between your current and your applied voltage. So let's say I sub D is your current, V sub D is the voltage across the diode, okay, which is like your applied voltage. No? This assumes that there's an excitation, and this is the voltage across the diode. We'll follow what we call the Shockley diode equation, and this is your Shockley diode equation. No? I sub D is equal to I sub S quantity E to the V sub D over eta V sub T minus 1. Where V sub D is your voltage across the diode, I sub D is the current through the diode. I sub S is what we call the reverse saturation current. This is the current that will flow if V sub D is negative. Take note that if V sub D is negative, this will approximately be equal to 0. If V sub D is negative, and if it is a relatively large value, this will be approximately equal to 0, and I sub D will be equal to minus I sub S. No? So this is your reverse saturation current, and this is the one due to this, no? Due to drift. Due to drift. The drift of the electron from left to right, and the drift of the hole from right to left. No? That's I sub S. And that's very, very small because it's due to intrinsic carriers. It will be anywhere from 10 to the minus 9 to 10 to the minus 15 amperes. And then you have your ideality factor, that is, this takes into account the processing. If the processing is good, then your ideality factor is equal to 1. If the processing is not good, then there's some degradation in the diode current. Your current will end up being a little bit smaller. Your ideality factor will be close to 2. And then V sub T is our thermal voltage, KT over Q, where K is Boltzmann's constant, Q is your electron charge, magnitude of your electron charge, T is temperature in degrees Kelvin. Okay, and V sub T, usually we use the approximation 26 millivolts at 27 degrees centigrade. So that's my last slide. Okay. Are there any questions? Okay, I think it might be hard for you to digest. So I suggest you go back to the notes and try to absorb this material. Also, if you're having a hard time, you might want to go to the reference for this course, which is Cedra and Smith, no? Microelectronics Circuits, Cedra and Smith. Okay. Okay, any questions? Okay, so I have to leave, no? Because I have a meeting at 4 o'clock. I probably can entertain maybe one short question. So I'm going to if nobody asks questions within the next minute or so, I'm going to have to close the session already. So thank you very much.
Thank you po, sir.
You're
Thank you,
welcome.
sir.
Thank you
Yes,
po,
sir.
sir.
Yes, sir.
You're
Sir,
welcome.
ako po
Thank
may
you po,
tanong.
sir.
Very short lang po, sir.
Sure, no
Tatanong-
problem.
Tatanong ko lang po yung regarding po dun sa drift and diffusion. Medyo nalito rin po kasi ako.
Okay,
Yung
okay.
drift po, wait lang, sir. Ibabalik ko lang po doon sa note ko. Ayun. Ang drift po, may sinabi po kayo kanina sa drift and diffusion na kapag high yung concentration tsaka low concentration. Which is which po doon sa dalawa?
Yung basta drift is due to electric field, no? Diffusion is due to difference in concentration. So nagkakaroon ka lang ng drift current kung meron kang carrier in the vicinity of the electric field. So that carrier will move. Yung diffusion, nagkakaroon ka ng diffusion when there is a difference in concentration of carrier in that particular area. So the carrier will tend to move from the area of high concentration to the area of low concentration. Pasensya na, no? Sometimes when I'm talking nababaliktad ko yung diffusion at saka yung drift, ano?
Bali, sir, yung sa diffusion po, nag-move from high concentration to low concentration. Tama
Yes,
po?
that's right.
Tapos
Oh,
po, it is due to the difference of concentration.
that's right. Oh.
Nung ano po ba to? Nung kahit ano or ng N-type or P-type?
No, basta for example, electrons, no? Pag mataas ang concentration sa isang area, ang tendency nun is yung electrons na yun pupunta dun sa mga areas na mas mababa yung concentration. Ganon din yung holes.
Papantayin niya po kumbaga. Pupunan niya yung mas maliit. Tapos po, yung sa
Yung analogy ko, yung tinta, di ba? Magpataka ng tinta sa tubig. After a while, nawawala na yung, hindi mo na makikita yung tinta kasi kumalat na siya sa tubig.
Opo. And
Yun
then
yung
sir,
parang analogy ko, no?
opo. Tapos sir, yung sa drift naman po, due siya sa electric field. So yung movement, yung electric field, ang galaw ng electron ay opposite sa electric field. Tapos yung
Yes.
hole ay parang nire-repel yung electric field.
Yeah, so basta't may electric field ka tapos may charge ka in the vicinity of the electric field and the charge is capable of moving, kailangan the charge is capable of moving. In other words, it has enough energy to move. Then- Kasi yun yung importante, no? Like electrons, pag valence electron siya, kahit na may electric field, hindi gagalaw yung charge, ano? Kailangan nasa conduction band yung electron para gumalaw sa electric field. So, yan.
Okay, sir. Yun lang naman po yun sa question. Thank you, sir.
Okay. Sige, sorry, no? I have to close the session now.
Thank you, sir.
Thank you po, sir.
Thank you po.
Okay,
Thank
you're
you
welcome.
po.
Sir.